And hello YouTube, hello fellow open formers. Okay, maybe you're not watching to do CFD in open form, but maybe some other kind of thing. But today we want to talk a little bit about some theory and background behind turbulence modeling. And today we want to talk, introduce ourselves a little bit to large eddy simulation. So hopefully you have some background on what Reynolds average Navier-Stokes is already. Okay, Reynolds average Navier-Stokes, you should know what that is. Basically, if let's say you take a point in the fluid, you have a pipe here, very long pipe, and there's some turbulent flow in there. You take a point at x and t, right? At x at some time, all right, and you try and average that velocity. Okay, so let's say your velocity is like this. Okay, there's turbulent velocity, and then you try to take a time average of that velocity, and that time average is a u bar. Time average. All right, and that's the general principle behind the Reynolds average Navier-Stokes. You do that for velocity in xyz direction as well as pressure as well, so you should be able to do that. Now, yeah, that has some good things because it's a very low cost computational way of modeling turbulence, and the net effect. I mean, you can go watch some other videos. I think over here there are some good videos for you to watch by some other people, but I'll make it short. I mean, yeah, I won't go into lengthy explanations, but yeah, the net effect is that, okay, it's a very, very good model because it saves a lot of computational power, and the only thing, just a recap, the only thing that differentiates, let's say, the mean velocity, the time average mean velocity from the actual velocity is this u prime thing. This is the residual velocity, right? This is the residual or the time varying part. The time varying velocity, and the long and short of it is that it gives rise to something called eddy viscosity. So for example, you see this equation I typed out here. It is u prime v prime. Okay, so when you substitute all this into the Navier-Stokes equation, just ignore this for now, the energy equation. You substitute all this expression back into the Navier-Stokes equation, you should be able to see all of these values popping up. For example, u prime, you have some average value of that. Okay, equals to u prime squared, and then you take the average. And then you also have this u prime v prime, blah blah blah. And how it's being modeled is that, okay, there's some turbulent viscosity. All right, there's some turbulent viscosity that it accounts for the overall effect on the fluid. And of course, you make a lot of assumptions to do that. But the net effect is that you have this viscosity that acts upon the fluid due to the turbulence. All right, apparent viscosity, so-called, so that when your fluid flow is like so. Okay, you have, I mean, laminar flow is this kind of a parabolic shape, right? So if let's say you have a turbulent flow, your profile is more or less like this. It's more flat. So where does this viscosity show? It shows that in the places where there is high velocity and turbulence. Okay, high velocity and turbulence. High velocity and turbulence, the fluid kind of becomes more sticky, so to speak. So that means this block of fluid tends to move as one cohesive cohesive piece, almost like plug flow, almost like plug flow. Almost like plug flow if you are taking a look at U bar. So this is a U bar, okay? So this is U bar. Okay, so that's the idea, is that we model the effects of turbulence but artificially, you know, inside the Navier-Stokes equation by so-called increasing its apparent viscosity or eddy diffusivity. Okay, some of the names are called eddy diffusivity. Okay, so they may use this form, or it may use this thing called turbulent kinematic viscosity or something like that. So that's how we model all these turbulent effects. And of course, there are models to do that. For example, the k-epsilon model, k-omega model, blah blah blah. All right, but the thing is that it doesn't capture flow separation very well. So what is that? Flow separation is generally like so. So let's say, especially for aircraft, flow separation is important. So let's say you have an aerofoil here, you have some flat plate or very thin flat plate. So there's some free stream velocity here coming in here, u infinity. All right, so it starts to touch this flat plate, and then it starts to have some boundary layer. And then after this whole shebang happens, after everything happens, there'll be some turbulence at the back, and you know, the flow will start to take off from the surface. Okay, so so that's when it's sort of like the boundary layer. Okay, so normally you have a boundary layer that kind of sticks to the surface, but then after a while, this boundary layer starts to go back into the bulk fluid. So that's what flow separation is about. Another situation you may see is in a spherical flow, where you have forced convection or something. You have some fluid blowing across a sphere or a pipe. Okay, so again, there'll be some boundary layer, but at some point, there'll be some some of the fluid will actually like take off, right? There will be some turbulence, especially in this part also, especially when you have you have eddies and you have backflows that cause fluctuations in the velocity. So these are what they call flow separation. Yeah, so flow separation, I'm not going to go in detail, but that's where you usually have a lot of vortices happening there. Okay, for flow separation. And usually it comes to generate a lot of vortices. Okay, it can be a turbulent vortex, which is usually the case when you have airflow over a plane, definitely turbulent flow. So that's what flow separation is about. And the k-epsilon model doesn't model this very well. K-epsilon model doesn't model this very well because it assumes isotropic effects on turbulence. It assumes isotropic effects on turbulence, and it models all turbulence that will increase the viscosity, apparent viscosity of the fluid in somewhat of a uniform manner. But that's not enough detail to examine something like this flow separation phenomena. So that's on one end of turbulence modeling. Okay, that's on one end of turbulence modeling. So you have the turbulent viscosity models. So turbulent viscosity models, and on the other end of the spectrum we have something called DNS. DNS is a direct numerical simulation, so that means it solves the Navier-Stokes equation in real time, and it will resolve every single bit of turbulence that happens on every single scale completely. But this takes up a lot of computation power. So this one, okay, this is one that resolves Okay, I'll just put here maybe a font size, or maybe I'll just zoom in. Resolves all turbulent phenomena. And this models all turbulent phenomena as increase in viscosity, eddy diffusivity, or turbulent viscosity. Okay, so that's where you find a k-epsilon model, etc. Somewhere in between is, okay, maybe I don't resolve all turbulent phenomena. Okay, I don't resolve all turbulent phenomena. So what the turbulent phenomena may look like, it may look like a lot of vortices or whatever, and the velocity is changing a lot. So you have lots of eddy flows, some big, some small, some very big. Okay, and DNS will resolve all of them. Okay, so what happens if, okay, I want most of the benefit of DNS. I want the accuracy, but I want to lower some computation cost. This is where LES, or large eddy simulation, this is where large eddy simulation comes in. So I say I only want to model the biggest eddies. So I model the biggest eddies. Only biggest eddies model. Why? Well, because the biggest eddies are the ones that they tend to carry the most momentum. And maybe in some other cases, heat or energy. Okay? When you talk about small eddies, okay, small eddies actually they dissipate a lot of energy. That's where most of the dissipation happens. Energy. And why is it okay, small eddies dissipate the most energy. Why is that so? Let's consider a small eddy like this. We will have a certain length scale and a certain velocity associated, right? And this will be u prime. Okay, so the Reynolds number, okay, Reynolds number equals to u into the length over some actual viscosity of the fluid. This is not turbulent viscosity, this is the actual viscosity of the fluid. So in a small eddy like this, okay, and in some of the smallest eddies, the Reynolds number of the eddy will be approximately equals to 1. So these are the times where the viscous forces are about comparable to the inertial forces, and the dissipation rate is so high that it starts to break the eddy up. So the eddy kind of disappears because the turbulent kinetic energy is being dissipated. So most of the dissipation happens here, but because they're small, the thing is, because they're small, they don't carry a lot of momentum, heat, or energy, let's say across the pipe. Let's say you have a pipe, or you have some fluid. Small eddies don't really travel far. Okay, small eddies don't really travel far, and they dissipate lots of energy, kinetic energy. Therefore, the assumption is that they don't carry most of the most of the momentum. So let's say you have a large eddy here. If it's swirling around in this fluid, and then there's a lot of convection going on because of this eddy current, or this eddy in the fluid, and along with the fluid, it will bring a lot of heat or energy around, or a lot of momentum around, so that yeah, these are the main transporters of heat and momentum. Whereas small eddies, they tend to dissipate very quickly, but at the same time, they also take up the most computational space. So this is why large eddy simulation has been invented. So I say, okay, I'm only going to model the biggest eddies, so that I can model my momentum and heat transport relatively well, even if they are not isotropic. Okay, like what this k-epsilon model kind of assumes is that this turbulence is isotropic, and that's not always a very good assumption. So instead, this LES model, it will resolve the biggest eddy. Sorry, I should use the word resolve. Okay, and it models the smallest eddies. Okay, maybe I should use type. It's a bit neater. So, models the smallest eddies. How exactly are the eddies modeled? They assume that, again, similar to the k-epsilon model, this turbulence in the smallest eddies will contribute to some sort of turbulent viscosity. Except it's not, the way of averaging is kind of different, but conceptually they are pretty much the same in terms that, okay, turbulence, the net result of turbulence is that, okay, the fluid's apparent viscosity will increase. So yeah, okay, so like I was saying earlier, you have this kind of flow profile. So one way of thinking of this flow profile is that there's lots of turbulence in the bulk bit of the fluid, right? Since there's a lot of turbulence, the fluid tends to travel together. I mean, the velocity profile here is pretty flat. So you can imagine the fluid at the center, bringing having very high shear stress on neighboring sections of the fluid. So let's say this section of the fluid has a velocity u. It will say, okay, I want the sections neighboring it to also have a similar velocity u, and you'll exert a lot of force on it. So that's what turbulence does, and that's why you kind of have this kind of a flow profile. So that's what turbulent viscosity is about, and LES will use this turbulent viscosity modeling on the smallest eddies, the ones which don't carry so much momentum, heat or energy, and they dissipate rather quickly. So in terms of computation power, this is less than DNS, but much more than having a turbulent viscosity assigned for everything. So if you're using CFD software, for example OpenFOAM will have a Reynolds average Navier-Stokes, which will fall into this category, and LES will obviously fall within this category. Okay, so the question now is, how do we do averaging? So I'd like to refer you to these three charts we have on the left. Okay, so this is how averaging is normally done for the Reynolds average Navier-Stokes. Okay, so let's say you have a true fluid velocity taken at some point x. Alright, so you have a true fluid velocity at some point x, right? And it's taken, and you see this velocity profile over time. It's fluctuating a lot, but at the end of the day, you take an average by doing this integral. So you integrate u x of t, x and t, x t, right, dt over some period. Period. E-R-I-O-D. So you integrate this thing over some period, and then you will get u bar, right? That's how we integrate for Reynolds average Navier-Stokes. And of course, in the period is up to you to decide. If you want a very long period, then you'll be pretty much doing a steady state modeling, because you don't model these fluctuations in velocity, right, over time. So if you make your period shorter, you can capture these bulk movements, okay, with a shorter period. So that it can capture some of the unsteady behavior of the fluid. I think some unsteady Reynolds average Navier-Stokes, they use this kind of thing, if I'm not wrong. So you can model the unsteady behavior if you shorten your period appropriately. Now, how about LES? How do you differentiate a large eddy from a small eddy? Because we'll have to, we'll have to separate out, what is a large eddy, what's a small eddy, which eddies do we resolve and which we do not. Okay, so in LES, this process is called filtering. Okay, this process is called filtering. So it's very similar to averaging. All right, so you don't resolve every single thing, every single bit of the velocity like DNS. So you do some sort of average for Reynolds average Navier-Stokes. For LES, this process is called filtering. And how does this filtering work? Okay, so instead of using time to average, as most frequently you have Reynolds average Navier-Stokes methods, they do that. They like to use time in that sense. You often find it. It may not always be the case, but often you'll find it's a time average of it. So this is quite simplifying the problem a lot. But yeah, for large eddy simulation, the way you average or the way you filter is you do it based on space. So for example, you have not u versus t, but now u versus x, where x is some kind of position. And then you have this pink colored velocity profile. All right, you have this pink colored velocity profile, and then you sort of do some averaging over the whole thing, and then you have this kind of smooth red colored velocity profile, which now this will become the u bar that we are looking for. Okay, this is what it probably might look like visually. Now, how do we write it mathematically? We know that the time averaging of velocity will look like this for Reynolds average Navier-Stokes, or most Reynolds average Navier-Stokes. So okay, we'll have a RA and S here. So U bar time average equals some integral over a period of U x t dt. All right, this is the Reynolds average Navier-Stokes way of doing things most of the time. But for LES, how do we do it? How do we do the filtering? So we integrate the velocity over some space, right? Over some distance, right? I mean, if we were to think of it conceptually, it could be like this. You could integrate the velocity xt across some distance, and you integrate with respect to dx. That's how, conceptually speaking, LES is slightly different, or pretty different from Reynolds average Navier-Stokes. Okay, so, but this thing is like, okay, maybe I'm taking this distance here. Okay, so at every point, I set myself a fixed distance for which to average the velocity. All right. Now, what if I don't want to maintain the same spacing throughout everything, right? Because if I want, let's say I want to use a bigger distance over here as compared to here. All right. So, I mean, LES does give you the not opportunity. It does give you some freedom to do that. So instead of using this, there's a more general way of writing this equation. So you might have seen this before. Okay, so I will give this a weighting function, right? I will give this I will add a weighting function to this u, x and t. Okay, so instead of using dx all the time, I'm going to use this function g. So what this function is saying is that, okay, cool, I can change my length anytime as I specify the size of this box throughout the the size of the averaging box throughout the whole, mesh or whatever, the whole domain. Okay, the whole space where I'm simulating the fluid, I can change the size of the box. And instead of using a simple average, I can say, okay, if I have the average I want to specify here, I can say the velocities here, I want to give it more weight as compared to the velocities here, which does make sense because it's supposed to represent a local velocity. So what do I mean? I want this, let's say I have this velocity, it's going at 5 meters per second, this one's going at 3, this one's going at 2, and then these are the boxes of velocities, right? I don't just do simple averaging. So 2 plus 5 plus 3 equals 10, and 10 divided by 3 equals 3.33. So that's like the ensemble average. Or this is just a standard kind of average, right? But But let's say I want to add some weighting factors to it. So I say that since the velocity here in the center is kind of more important, right? So I'm taking the filtered velocity at this point here. So the velocity closer to this point where I'm talking about is more important. So this is what I'll do. Maybe I would, instead of giving them all equal weightage, I'll maybe giving this 2 at the side a weight factor of 0.2, plus I have 5, 0.6, and 3 into 0.2. All right. So this way, instead of giving a weight factor of 0.333 to each of these, okay. So because I'm doing to get this 3.333 seconds is actually 2 times 1 over 3 plus 5 times 1 over 3 plus 3 times 1 over 3. That's how I get this average of 3.33 meters a second. If I want to assign a weight factor, I can do that. I just have to make sure all of these weight factors, when I sum them up, they should be equals to 1. So that's all I need to consider when I sort of add a weighting factor into this. So I have 0.2, 0.6, and 0.2 here. All this should sum up to 1. All right. So 2 times 0.2 is 0.4. 5 times 0.6 is 3. 3 times 0.2 is 0.6. And then I add this up, I'll get 4 meters a second, which is pretty much closer to this 5 than, let's say, this 3.333. So that's one of the ways to do averaging as well. You can add weighting factors, or you can adjust the size of your box, so to speak. And you can do it across the whole length. This is what this form is trying to say. Okay, so when you first see this kind of thing, it may look a little scary for sure, but what it's basically saying is that, okay, let's take some distribution u with respect to x, okay. Now this is one dimensional. You can do it across 3 dimensions of course. And let's say, okay, right, I want to take the point, the filtered velocity at some x value, right? So this is not time averaging, this is distance averaging. So I want to do this. So how do I do it? Let's say I have some point x1. Okay, I take this point, right? So that fixes your x value. All right, that fixes your x value. So the u of x here is fixed, right? But you also kind of want to consider the surrounding velocities. So if I fix my x variable there, so this is u of x, and I want to consider other velocities across the whole with respect to this point, right? I want to consider velocity in the periphery of this x1. Which was what I was doing just now with that numerical example. I'm considering velocities in the periphery of that x1, of this point. So yeah, what do? I can use another variable r to denote length, right? So if I fix this at ux, this is then u x plus some distance r. All right, so I will fix this point and I'll say, okay, I want to vary the distance around this point. So I'll use this variable r. So here is ux plus r, and then here, this one is u of x minus r. Okay, so this is where this r actually comes in. Okay, so of course where r equals 0 is where x, then that means it's 0 meters or 0 distance away from this x1. If I have a positive r, that means I want to have some deviation from this x1 in the positive x direction. If not, I want to do it, if I want to subtract r, I can do it in the negative direction as well. Oh yeah, I think I got my signs a little mixed up. This should be a plus. This should be a plus, this should be a minus. Okay, so that's just a basic transformation in graph theory. Okay, this should be minus if I'm not wrong. Hopefully I don't make another careless mistake of sorts. Yeah, I think I forgot all my things. But yeah, generally this r is just there to say, okay, I want to consider velocities in the surrounding of r, of this immediately peripheral to this point x1. Okay, so that's what this r is for. So this g actually gives us the weighting factor, g of r. Okay, so if we have a g of r, it gives us some weighting factor. Remember I was talking about weighting factor, where we have, let's say I want to give this central point more weight than these two peripherals. So let's say we have, all right, g of r, or maybe I can do something like that. R, I can put g of r. All right, and let's say I want to only do a simple box, right? If I have a simple box kind of a case, g of r versus r is like that, and you have the area. Okay, G of R is like some weighting factor, remember? So G of R is, you can sort of consider it like a PDF, probability density function of some sort. Okay, so this is a simple average kind of a shape. You have a simple box where we have, let's say, even distribution, even weighting of all velocities in the vicinity of x, or x1, as we were talking about earlier. We have a box average, then G of R will look something like this. The weighting factor is equal. So this G of R is the weighting factor. Okay, let's say I want a different shape. What will it look like? So we have R, G of R. Okay, we have a R and G of R, and we can assign, let's say, a different weight system. Okay, let's say a bell curve. Now this is called Gaussian. So G of R can be a Gaussian distribution. Okay, so I'll stop here. And yeah, I'll continue more in the next video. Thanks for watching. I'll see you guys again.